Today we're going to use Ampere's law to find the magnetic field produced by a toroid. So we need to remember first what is a toroid. So essentially a toroid is a solenoid, which we talked about in the last video, that has been bent into a donut shape. Now the shape of this donut doesn't really matter that much as long as it's symmetric all the way around. So let's set up the problem. We start with two concentric circles to represent our toroid. So we'll draw them like this, and we'll say that the first one, the inner circle, has radius A, and the outer one I won't draw a line across so it doesn't get confusing, but we'll say that it has radius B, the outer circle. So what a toroid is we say that we have a wire that comes in and essentially wraps around this donut shape all the way around, just like a solenoid that has been bent into a circle. So I'll draw the wires in. And then we run a current through this wire so that it wraps around all the way around so that it comes back out on this side, and we'll say that current is I. And we'll say that there's a total of N loops of wire. So N loops of wire all the way around that all carry current I. And so then what we want to do is then find what is the direction of the magnetic field produced by this toroid. So similar to what we did for the solenoid, we can take a few of these wire loops and study them all individually, and then join them together as a whole at the end to see what the total effect would be. So we have the current flowing this way in each of the wires to this direction. And with the right-hand rule, we can say if we put our thumb in the direction of the current, the magnetic field will curl around the wire. So it will curl around like so in each of these wires. And this is B. And now, similar to the case of the solenoid, each of these wires individually is going to have a certain B component that cancels with the other one. And the overall component that does not cancel is going to slowly curve around with the curve of the toroid. So what that means is outside of these wires, outside of the toroid, we're going to have a steady B that curls around like so. And inside is going to go the opposite direction and curl around like so as the B inside the toroid. And that's because at each of these points here, this is going to cancel with this part of the magnetic field produced, this one with this one, etc., etc. And inside, we're going to have an overall net direction that curls this way, and outside, it will curl that way. So in conjunction with Ampere's law, which we can write in its closed form, and a unique choice of an Amperian loop, we can find out what the magnetic field is produced by this toroid. So now that we've figured out what a toroid is and set up the problem in this diagram, and we have Ampere's law saying that the magnetic field dotted with the infinitesimal line element is equal to mu naught times the enclosed current by some Amperian loop of our choice, we can choose what this Amperian loop is in order to exploit the symmetry of the toroid and figure out what the magnetic field is outside and inside of the toroid. So let's start with the magnetic field outside of the toroid. So we can draw our Amperian loop completely outside of the toroid. And we can say it's at radius S. And similar to the case of the solenoid, where we had the Amperian loop completely outside of the solenoid, what this means is that there's actually no current that's going to pass through the Amperian loop surface. So the I enclosed is 0. And what that means is if we work through this integral and we figure out that this is equal to mu naught I enclosed, which is equal to 0, we can simplify fully to say that the magnetic field everywhere outside of the toroid is 0. And this is similar to what we did in the solenoid case, where we said that before, that the magnetic field would be curling around like so, if it existed, but because we found out the magnitude is equal to 0, that means that at this point inside of the toroid, so inside of the donut, and everywhere outside, so that is where S is less than A, unless S is greater than B, saying that we start at 0 in the center here. The magnetic field will be 0 everywhere that S is less than A and S is greater than B. And all that's left to do to figure out the rest of the problem is to find what the magnetic field is inside of the toroid. So to find out what the magnetic field is inside of the toroid, we'll choose an Amperian loop, again of radius S, such that it passes on the inside of the toroid, like so. So we'll say this is our amp loop. And then we can look at Ampere's law in its integral form and start with the right-hand side of the equation where we find out what is the enclosed current by this Amperian loop. And so this Amperian loop will pass through every single one of these turns of wire. And at the beginning of the video we said that there were n turns of wire, n loops of wire. And each of these n loops is carrying current I. So therefore the entire enclosed current by our Amperian loop, which passes through every one of these wire turns, is just n, the total number, times I, the current that each of them are carrying. So we can take one step further, saying that the closed integral of the magnetic field dotted with the infinitesimal line element is simply mu naught times n times I. So now to finish the problem, we look at the left-hand side here, which we find out the magnetic field and the infinitesimal line element. And we can do that by drawing our Amperian loop like so. And we said at the start of the video that the magnetic field inside of the toroid is going to curl around in this direction, like so. And we can choose the line element such that dl will also point in this direction all the way around the Amperian loop. And so that means that at all points, B, the magnetic field, will be parallel to the infinitesimal line element, dl. And this will simplify this integral because we know that for two parallel vectors, the dot product simplifies to be the magnitude of both of those vectors, n times I. And the magnitude of B will be constant or the same at all points around this Amperian loop, so we can pull that outside of the integral. And now simply we have to find what this integral is, solve for B, and the problem is complete. So we can work through saying that the Amperian loop has circumference 2 pi s is equal to mu naught n times I. And finally we end up with the final magnetic field produced by the toroid, where we say that mu naught n I over 2 pi s, and it will curl around the toroid, which we can express as the phi hat direction vector. This is for points inside the toroid. And then it will be 0 for points outside of the toroid. So the final magnetic field produced by this toroid, of course, has magnitude 0 at all points inside the toroid and outside the toroid. And when I say inside, I mean inside of the actual donut itself. And it has mu naught n times I over 2 pi s in the phi hat direction. It has that magnetic field at points inside of the donut, inside of the toroid, where n is the number of loops or turns of wire that are carrying current I, and s is this radial distance away from the center of our origin at points ranging between A and B. So we can say that inside means A less than S less than B, and outside would be S less than A and S greater than B.